So anyone knows that whenever you are doing ordinary differential equations solving linear ODEs, then it's pretty straightforward. So a linear ODE, and I know this is nonlinear, we're talking linear for a second. Linear ODEs look something like this. Y equals some g of x. So if you have a linear ODE, what you can do is you can guess, well, first of all, you're going to solve the homogeneous version of this problem, homogeneous version. So in this case, you'd solve y homogeneous plus f of x, y homogeneous equals 0. And then you guess, for your main problem, you would guess the solution of y equals u times the homogeneous solution, okay? So basically, that's that. Now, that works for linear ODEs always. Well, first order linear ODEs always. Then whenever you're looking at nonlinear ODEs, at this point, it's kind of a guess and hope method. I don't have a better solution, but for the moment, your best strategy is a guess and hope strategy. So basically, a nonlinear is going to be anything that doesn't look like that. So a nonlinear might look like, f of x and y times y plus g of x and y, something like this. So that means that you can have y's, you can have y squareds. See, in this one, you couldn't have a y squared. That would not be allowed. You couldn't have an e to the y. That would not be allowed. But over here, you could have e to the y, you could have y squared, you could have y to the negative 4/3, and all those are perfectly happy. Unfortunately, that means that guessing solutions for them is that much harder. So basically what we're going to do is we are going to try to come up with some basic strategies for solving some nonlinear ODEs. So there's a couple of ways that you can do this. There's two that we're going to mention. So, well, we'll call 3 strategies, and the third strategy is kind of sad. But there are 3 strategies. One is hope for Bernoulli. So if you have a Bernoulli equation looks like this. Y prime plus p of x y equals f of x times y to the r, and r is an integer. Or I think it actually could be a real. I'm just going to say integer, real maybe? I don't know. But at least definitely an integer. Any Bernoulli equation can be solved by this method as well, or the previous method of solve the homogeneous and then guess, except I can't spell. So solve the homogeneous method and guess that y equals some unknown function u times the homogeneous, and then just figure out what u is by plugging it back in. So that's your first strategy, is to hope for Bernoulli. The second strategy is to see if you can rewrite in terms of y over x. Rewrite like this. I'll say rewrite like this. So if you can rewrite it such that y prime is a function of y over x. So say you're able to write something and it's like y over x plus e to the negative y over x plus 3. We'll say y over x to the negative 1. Maybe it was x over y, but it's y over x to the negative 1. So if you can rewrite a diffie-q in all terms of y over x, then what you're going to guess is y equals ux. Okay? So then the third strategy, unfortunately, the third strategy is guess randomly and get it right for the moment. Okay, this is just what we have for the moment, and get lucky. So we're going to look at a couple of those strategies here and the other videos in this little section, this little playlist. So really what you're wanting to look at is if you have a nonlinear equation, you can hope that you get a Bernoulli, you can hope that you get a y over x, and if you don't get something like that, then you just want to kind of guess randomly and hope you get lucky. So we're going to go take a look at those. All right, so let's go for this. So the first one is hope for Bernoulli. So let's assume that we have ourselves a nice little Bernoulli equation. So this is one, is Bernoulli. It's not really a playlist, it's just a group of video, or just a one video really. So Bernoulli. So let's say that we have something like this. We have y prime minus y is equal to xy squared. Now, for this one, we can't separate this. There's no way that we can get all the y's on one side and, well, not without the minus sign. We can't get this written to where it's like blah, 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 dy equals blah, 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 dx. Just can't do it. So basically what we have to do is we have to find another solution. So this is not possible. We can't make this separable. So we'll say not separable. Not separable. However, it is Bernoulli. Not separable. No, it is Bernoulli. So that means that we're going to solve for the homogeneous, and we're going to guess y equals u times a homogeneous solution. So that'll be amazing. Sorry guys, my voice is out this week. So we're going to solve the homogeneous solution. So if you think you kind of know what we're going to do, pause the video and see if you can actually get this done. If not, just go ahead and watch along. But to solve for the homogeneous solution, basically that means we're going to take the left side of the equation, y homogeneous prime minus y homogeneous, and set that equal to 0. So we've got y homogeneous prime equals, well, y homogeneous, so that's dy homogeneous. Well, I just know the general solution to that because this matches a whole bunch of stuff. In fact, I'll just even leave it here. The general form to this kind of a problem is y homogeneous is the constant times e to the negative coefficient in front of here. The coefficient in front of here is -1. So negative -1 dx, or in this, yeah, dx. So we've got y homogeneous is equal to c times e to the integral of 1 dx, which is just 1 e to the x. So what we're going to do is, for our original problem, we're going to guess, we're going to guess y is equal to some unknown function times e to the x. So that's going to be our guess. Okay, so what we're going to do is we're going to take the derivative of that, and we're going to say, okay, so if y is equal to u times e to the x, that means that y prime is equal to u prime e to the x plus u e to the x. That's kind of fun. What we're going to do is we're going to substitute in for y prime to the original equation. We're going to substitute in y in the original equation in all the places that it occurs. Okay, so, all right, so we're going to start off with y prime. We know that y prime is u prime e to the x plus u e to the x, and we're going to subtract off y. Y is u e to the x, and that has to equal x times, again, y, which is u e to the x squared. Okay, now we're going to simplify, and hopefully if we've done this correctly, a lot of things should cancel out. So u prime e to the x plus u e to the x minus u e to the x, well, clearly that's going to cancel, equals x times u squared e to the 2x. This is going to go away, and this is going to go away, and makes us super duper happy. And so on the left, we've got u prime e to the x equals x u squared e to the 2x. So that's going to go away with that. Now, you will see that you'll have a separable equation. I've got u to the -2 du equals x e to the x dx, like that. And then I can come through here and I can integrate both sides because it's officially separated. I can integrate both sides. On the left, I've got -1 to the u to the -1 equals, oh, this is stupid. This is something I have to go do off to the side because I don't remember how to do this. So anyway, I got the left-hand side. On the right-hand side, this might be an integral that you recognize. In case it's not, I hate doing a u substitution, but because we've already got a u, so this is a, call this an aside. This is a totally different u, not the same u. I don't want to switch variables on you because I'm afraid if I say udv or vdw equals uw to minus blah blah, that's just going to confuse you. But you probably learned at some point that integral udv equals u times v minus integral v du? Sometime, long time ago? Okay, so we're going to do the same thing here. So in this case, our u is equal to x, and our dv is equal to e to the x dx. So that means if u equals x, then du equals dx. And if dv equals e to the x dx, then that means that v is equal to e to the x, because if I integrate both sides, I'll get v and e to the x. So I can say that this equation here is equal to, or basically that x e to the x dv, or dx, is equal to u times v minus the integral of v times du, and that's just e to the x like that. So this is some Cal 2 probably, so just helps you figure that out over there on the right hand side of this equation that we're missing. If you don't remember, this is called, I think this is called integration by parts, maybe? If it's called that, then great. If not, Google something else until you figure it out. But in any way, we were able to get that answer right there. So on the right hand side of my equation that I was originally working on, I've got that integral is equal to x e to the x minus e to the x. And if you take the derivative of that, so if you just want to check, if you really don't believe me, you can always check. If I d dx this, I get product rule, and then x e to the x, which is what I had originally. So it does work. You just might have to prove it to yourself. But in any case, trying to remember what we were doing in the first place, I've got negative 1 over u is equal to x e to the x minus e to the x, or that u is equal to 1 over e to the x minus x e to the x. And again, why did I care what that was? Well, oh, I need a plus c somewhere. Here, plus c, plus c, plus c. And again, it doesn't matter what happens to the plus c, I'm just throwing it under. The whole reason that I care is my original guess. If you remember, if I go back up, here's my original guess, is u times e to the x. So y equals this times e to the x, and that is my final solution to that original differential equation. So we say that this solves whatever we had before, y prime minus y equals xy squared. So that's the solution. So basically the idea is you recognize that it's Bernoulli, you solve the homogeneous, see how it goes, and then end up solving for u. That's kind of fun. Okay, so that's one option. Now, for your second option is hope for y being a function, or y prime equaling a function of y over x. Okay, so that's your second strategy in solving, in trying to turn a nonlinear ODE that's not separable into a separable ODE. So remember that in this case, if this happens, if we can rewrite the function in terms of y over x, then we're going to guess y equals u over x. And that's actually kind of easy to remember because it's really guessing u is equal to y over x. So I feel like I said that, but it's weird. Anyway, is that's what we're guessing there. So say we have a problem like this. So say we have y prime is equal to y plus x e to the negative y over x divided by x. Now looking at this, there's absolutely no way that this is separable. It's not linear. I can't get all the x's on one side and all the y's on the other side. It's just not going to happen. But I see these y's over x's, and so it kind of gives me some hope. So if I divide each individual term, then I clearly can see that I can write this in terms of y over x. Okay? So this means that I'm going to guess a solution of y is equal to u times x. Now, again, all I'm going to do is I'm going to take that guess and I'm going to plug it into the original equation and see how far along I can get. Okay? So, y prime, again, if you think you know what you're doing, pause the video, see how far you can get. If you just want to watch, that's fine too, but you learn more by doing. Y prime, or u prime x plus u, x prime is just 1. So I'm going to go ahead and plug in it's going to be a little bit faster if I use the fact that u is equal to y over x, and then I plug into this on this side and go from there. So y prime is u prime x plus u, and that's going to be equal to y over x is u plus e to the negative y over x is u. And again, you see that these u's cancel out, which means I probably did something right. I've got u prime x is equal to e to the negative u, which is kind of fun. And so if I move this to this side, I've got e to the positive u prime equals x, eu du equals, 1 over x. Sorry about that, guys. 1 over x. 1 over x dx. Integrate both sides. On the left, I've got e to the u. I'll put the somewhere. E to the u equals natural log of x plus c. And then u is equal to y over x. And so now I actually have a full solution in terms of x and y. Now, I can leave it like this. This is called an implicit form, which means that I've kind of implied what the value of y is, but I haven't actually solved for it. If I wanted to solve for it, I could. I could just come over here and take the natural log of both sides. So I get y over x is equal to the natural log of x. And I'm going to go ahead and put in my absolute value signs to be good, plus c. So, and then multiply both sides by x. So this is another form of the same solution. This is called the explicit form because I'm explicitly telling you what y is. All right? Okay, that one's a little bit different, so just to give you some practice, let's do one more. And one more. So this is definitely one where if you're still following along at this point, I would say pause the video and see how far you can get. So start off with x squared y prime plus y squared plus xy minus x squared. So looking at this immediately, you can tell that it's nonlinear, but we're still trying to figure out what to do with it. So your first step should really be to say, okay, well, I'm going to see if I can rewrite everything in terms of y over x, of y prime equals y over x. And if I can do that, then that means I might actually be able to do something interesting here. So pause the video, see how far you can get. Okay, so let's pretend that you did that. Yay. So my first step is going to be to divide the whole equation by x squared. I've got y prime is equal to y over x quantity squared plus y over x minus 1. Yay! So that means that I can guess y equals ux. And that's kind of, like I said, easy to remember because basically I'm guessing that u is y over x. So again, that means that y prime is equal to u prime x plus u times x prime, which is 1. So I'm going to go ahead and I'm going to plug that in. So I've got u prime x plus u is equal to u squared plus u minus 1. Lucking out, the u's cancel out. So that ends up with u prime x equals u squared minus 1. And so I can divide both sides by u squared minus 1 equals 1 over x dx. Now as you look at this, you might say, okay, but I don't know how to integrate that. The answer is yes, you do, because you're amazing at life. So if you got this far and you got stuck, pause the video. I'm going to give you a hint. The video is partial fraction decomposition. Okay, so did you get that? The little trick hint thingy, partial fraction decomposition? Again, something that if you're not good at, you definitely want to get good at before you get too much further along in decomposition. Because it's going to come up a lot for integrating and then for Laplace transforms, which is kind of the penultimate experience of a first class in ordinary differential equations. So partial fraction decomposition means if you're trying to integrate something and you see on, like you have right here on the left, and you see that you can factor it like this, so this would be u plus 1, u minus 1, then that means that you can separate it out like this. So you have u plus 1 here, and a u minus 1 here. And you know there's coefficients a and b. So I'm going to go ahead and I'm going to multiply through the whole thing here by u plus 1. u minus 1. Whenever I do that on the left, I get 1 equals a times u minus 1 plus b times u plus 1. Now, there's a couple of different ways that people do this, but probably the easiest way that I've ever found is to start off by letting u be something that just makes stuff cancel out. So I could let u equal positive 1, for example. And if I do that, then I get 1 is equal to a times 1 minus 1, which is 0, plus b times 1 plus 1, which is 2. So I can say, okay, well, b is 1 over 2. Then I can let u equal negative 1. And again, the reason that I would do that is so that one of those terms is going to go to 0. So I have 1 is equal to a times negative 1 minus 1, negative 2, and b times 0, or a is equal to negative 1 half. So that means that this here is going to be equal to negative 1 half u plus 1 plus 1 half u minus 1, which is good because I can integrate that easier. So that's what we're going to use. So over here on the left, I'm going to integrate negative 1 half u plus 1 plus 1 half, and I'll go ahead and separate those out, plus the integral, no specific reason except I just think maybe it'll be easier to follow. And then the left side integrates to natural log of x, and this way, like this. Natural log of x plus c, I guess, because we need a plus c somewhere. I can pull the negative 1 half out, but 1 over u plus 1 is going to come out to integrate to natural log of u plus 1. And then the next one is going to come out to the natural log of u minus 1. And I'm going to probably go through here and I'm going to multiply the whole thing by 2 just to get rid of those stupid 1 halves. So I've got natural log of u minus 1. I'm just switching the order so the negative comes first. U plus 1 equals 2 natural log of x, and then it's just a constant, so 2 times a random constant is still just a random constant. Now I can combine my natural logs, since they're being subtracted, into u minus 1 over u plus 1. So as long as u is not equal to negative 1, I'm in good shape. Or as long as that whole thing in general isn't, whatever. Anyway, so I've got e to the 2 natural log of x plus c is equal to u minus 1, u plus 1, like that. So that's kind of fun. I can make a little bit more progress in simplifying this. I've got a constant times e to the 2 ln of x is equal to, now remember that u is just y over x. And of course, here I can just move this 2 to be x squared, and the e to the natural log of x squared is just cx squared is equal to y over x minus 1 over y over x plus 1. And there I've got a really lovely implicit solution for my differential equation, for my nonlinear differential equation. So I promised you a third method, and that third method is the lucky guess. And it would be really great if there was another method besides the lucky guess. There actually is, but we're just going to go with the lucky guess for the moment because it kind of fits into what we're doing. So let's pretend we can look at this just absolutely embarrassing nonlinear ODE and say, you know what, I'm guessing that the solution is in the form of y is equal to u times x to the 1/3. I don't know, but you just figure it out, so way to go. So anyway, so that's a lucky guess method. So go ahead and see if you can solve this using the lucky guess method. So I'm going to tell you this is the right guess to make, but go ahead and just for the practice, go through the calculus of putting it together, substituting it into the original equation, and see how far you can get. Alright, so again, last time we'll pretend that you did that. So y prime is equal to u prime, x to the 1/3, plus 1/3 u x to the negative 2/3. Yay for, calculus. Alright, so 3x y was u x to the 1/3 y squared, times y prime, is equal to y cubed plus x, like that. Yay! Okay, so I've got 3x u squared x to the 2/3 times a bunch of stuff. I'm just going to do algebra for a while. You don't need me to narrate. Algebra equals algebra. Algebra's fun because it makes me happy. So I have x times 2/3 x. So I'm just going to make that 5/3 x. I don't have to write the whole thing out again. Alright, so I've got distributing, I forgot that, u squared, x to the 6/3, which is 2, u prime, plus that, u cubed, 3/3, which is 1. Ooh, yay, stuff cancels, because if it didn't, I'd be scared. Not like scared, because I'm tougher than that, but, it'd be something that goes away. Alrighty, so I've got 3u squared x u prime equals 1. 3u squared u prime equals 1 over x. So 3u squared du equals 1 over x dx. Integrate both sides. U cubed plus c equals natural log of x. So e to the u cubed plus c equals x. U cubed was something. What was u? I guess, I didn't know what u was. I don't want to solve for x or u, I want to solve for that. So u cubed, or u equals natural log of x plus c doesn't really matter because it's plus c or minus c to the 1/3. And then my guess was y was u times x to the 1/3. So if I've got this to the 1/3 times x to the 1/3, then I've got a lovely final solution of, well, x times natural log of x plus c all to the 1/3 power. Yay! So it's really not that pretty, but it's a solution. But we're actually going to show another way to solve. So really, the only reason that you would use this is if you're guessing and you're trying to make it separable. So the lucky guess method really isn't something that you're going to use a whole lot. Better than lucky guess. So we'll say lucky guess is clearly not the best strategy. The lucky guess is really going to give way to looking at what we call exact equations. So we're actually going to solve this exact same problem again in a little bit later in another video, obviously. This has kind of gone off in a life of its own. But we're going to solve this same problem using the method of exact equations. And if you're looking for it, another thing to look up is integrating factor. And that's just another way to solve differential equations without making them separable. So all three of the methods here that we discussed depend on you being able to separate it by guessing for like a u kind of thing, but we're not going to do that in some of the future strategies and other ways of solving diff EQ.